makes me accountable.
Because then the whole world could see you not logging in.
All right. That's what it is. Dude, I just started streaming.
Oh, shit.
Jesus Christ. No. Oh my good God. Nothing happened.
Why? I don't have a voice like that. Alright, I'll leave it alone. You gotta lock in. Stream makes you accountable. Stuff and things.
Stuff and things. Okay.
Totally. Never mind. I'm leaving. I'm leaving.
Alright. Let's lock in. So he went over linked list. How do you say that? Resizing arrays, dictionaries, stacks and queues. Okay. And then the next part I'm at is trees, apparently. So this is probably going to have to do with how linked lists are going to be actually useful, because right now they don't seem useful. You can add stuff to a linked list, but it has to go in the order of the linked list, and you can't change it. But this linked list stuff is like, woo, man, it's not easy. It's like, it's a basic concept, but when you turn it into code, I mean, it's like everything. When you look at it in code, it's so much to look at, you know what I mean? And like to draw, I mean, I guess drawing it out looks so much easier than seeing it in code. Anyways, it's a lot. Here we are.
All right, we are back. So let's recap how we got here and why. So we started with our old friends arrays, which we introduced in week 2, and recall that the whole appeal of arrays was that, one, as all things go, like relatively simple, certainly now in retrospect, but more importantly, they were really darn fast. Like arrays, insofar as they are stored back-to-back, contiguous in memory, means that we could do very simple arithmetic recall to like figure out the length of it, and then divide by 2 to get the middle, divide by 2 again to get the middle of the middle, and so forth. And even though we might have to deal with a little bit of rounding, arrays lent themselves to binary search and thus logarithmic time, so big O of log n. But today I claim that the downside of arrays is that you have to decide in advance how big you want it to be, and if you guess wrong and it's too small, how much memory you ask for, you then have to reallocate memory, and that's fine. It's solvable with malloc or realloc, but it's going to take some amount of time to copy all of the old memory into the new memory, whether you do it with a for loop or realloc does it for you. Meanwhile, we only did it with like 3 values, maybe 4, but imagine it being 3 million values that you now need to allocate more space for. You're going to waste a huge amount of time copying 3 million values from the old location to the new, and so that's just generally not very appealing. And so that motivated our whole discussion of linked lists, whereby now we can create a more dynamic data structure whereby we only allocate memory as we need it. So we don't have to worry about underestimating or overestimating and therefore wasting memory. We can just go bit by bit for each new value. We allocate another node, another chunk of memory, and the thing just grows and grows and grows. But as we saw just before break, the downside is even though we're avoiding the inefficiency of having to move stuff around in memory, once allocated, the nodes can stay where they are and we just update our pointers. All of our running times for searching, inserting new elements, deleting old elements would seem to be big O of n. But why was that? Well, in the context of a linked list, recall that it might look a little something like this, whereby we have a pointer called list pointing to maybe 4 values like this, and suppose that we do want to search for a value. Now it's nice because in our latest version of this linked list, it was sorted from smallest to largest, and that was always a precondition of doing binary search. But even though it's obvious to our human eyes where the middle is, it's like roughly over there, how is the computer going to figure that out, or how is your code that you write? Well, unfortunately, the way we've stitched a linked list together with these pointers is if you want to find the middle, you can, but you got to start at the beginning, traverse the whole thing to figure out how long it is, then do it again and stop halfway through, once you know what the halfway point roughly is. Then if you want to search the middle of the middle, you've essentially got to do that whole process again. And so now, just to use binary search, you need to spend big O of n steps just to even find the middle. Now if your mind is kind of spinning and you're like, well, maybe I could just kind of cheat and use a pointer to always point to the middle of the list, totally fine. You can spend some additional space to remember the middle of the list, the end of the list. But where does that stop? What if with binary search you go not just to the middle, but the middle of the middle, the middle of the middle of the middle, the middle? Are you going to keep around a pointer to every element? Because if you do, you're essentially back to an array if you've got one location for every other location. So it just kind of devolves into a mess, even though there's some minor optimizations we could in fact make. In fact, we didn't talk about it yet, but one common alternative to a singly linked list, which ours is, it's linked with a single pointer from node to node. Computer scientists also like to talk about doubly linked lists, where there's arrows going both directions, which actually would have simplified some of the last code that we looked at, because I don't have to look ahead to figure out what I want to free or what and where I want to insert some value. But that too doesn't fundamentally change the speed. It just makes your code a little easier to write. So in short, with linked lists, we get dynamism. We can now grow and shrink things without wasting time copying, but we've lost hold of our binary search. And that was very appealing as far back as week 0 when we wanted to do something quite quickly. So let's see if we can't make some mashups now. Take some arrays, take some linked lists, literally mash them together into a sort of Frankenstein data structure and see if we can't get some of the speed of arrays, but the dynamism of linked lists. And so I give you trees. If you think about in your mind's eye what a family tree looks like, where you typically have some parents and then some children and some grandchildren and so forth, it's this sort of tree-like structure, even though by convention it's drawn top down instead of bottom up like trees in the real world. But the top of that family tree, we're going to call the root of the tree. It just so happens to indeed grow down. But a tree is a very common data structure, and it's interesting vis-a-vis arrays and linked lists in that it's the first of our two-dimensional data structures. An array is effectively just a single dimension along from left to right. A linked list is essentially the same, even though in reality it might be up, down, left to
Baby wants my attention 24/7.
right. In memory, it's still just one thing stitched together in a single dimension. A tree adds now a second dimension, and specifically useful for us is what we're going to call binary search trees, which is, spoiler, going to give us back the ability to use binary search, but we're going to store the data a little more cleverly than in arrays.
What? Being a butthead. She doesn't want juice. She's just saying she wants
Her juice was in here. It was in here. Where'd it go?
Her juice?
Yeah.
Oh, really?
Yeah.
No, that's mine.
Where's her juice?
It's right here. I knew it was here.
Oh.
Did you just grab your own hand? You want it?
Yummy.
You want it? You want it? You want it?
Oh.
Come on.
She's so needy.
Come here.
I'm just watching this. You're gonna not be into this.
Alone. Instead of storing our data in one dimension, in a binary search tree, we're going to store in effect in two different dimensions, and that's going to gain us some speed. So here, for instance, is an array of 7 numbers, as we might have seen it back in week 2, when we first introduced arrays. Let me draw our attention to the middle element, and then to the middle of the middles, and then the middles of the middles of the middles, just by color coding them slightly differently. If I were to run binary search on these numbers, or the lockers that we had on the stage a few weeks back, I would jump to the middle, then the middle of the middle, and so forth. The catch, though, is that implemented as an array, it's not going to be very easy to add new values. Why? Because if I want to add the number 8 or 9 or 10, I might get lucky and there might be room in memory here, but I might get unlucky, in which case then we got to start jumping through those hoops of malloc or realloc and copying all of this memory to a new location, which is doable. We solved it in code, but it's going to be slow for larger data sets. So can we avoid that? Well, maybe. I deliberately color-coded things like this because let me propose that instead of storing these 7 values in an array, let's store them in a family tree-like structure like this, where I just kind of exploded them vertically on the y-axis here. So now the middle element, the 4 is at the top of this tree. The 2 and the 6, which were the middle elements, after the middle are going to be to the left and right of the 4, and then these leaf nodes, so to speak. We borrow a lot of vernacular from the world of actual trees. These are leaves in the sense that they themselves have no children. They're at the edge of the data structure, are going to be the middles of the middles of the middles. But all of the data is still there. I've just exploded it from 1 to 2 dimensions, and let me propose that now that we have this technique of using pointers, which we use with C code, but you can depict them pictorially with arrows, let me propose that we stitch together these 7 values in memory using a bunch of pointers, whereby now each of these nodes, drawn as a single square for simplicity, is going to have not only an integer associated with it, and not just 1 pointer, but per these arrows, as many as 2 arrows associated with it. So our nodes are about to go from data structures with 2 things, a number and a pointer, to 3 things, a number and 2 pointers for the left and right child, respectively. And I dare say now that we have a 2-dimensional tree data structure, consider how you might find a number therein. Suppose I'm searching for the number 5. Well, I start at the root of the data structure, and even though our human eyes obviously know where we're going, notice what's important about this binary search tree. If I go to the root of the tree, I see the 4. 4 is obviously less than 5. What does this mean? This means I can divide and conquer the problem right off the bat. I know that 5 is going to be to the right of this node, which means effectively, if you think in your mind's eye about snipping the branch there, I have just halved the problem, essentially, like dividing the phone book in half. Why? Because I don't even waste time looking at this subtree, the left child of the 4 element. Meanwhile, if I go from the root to its right child here, I see the number 6. 5, of course, is less than 6, so this is effectively like snipping off that child because I don't need to go further there because I know a smaller element is going to be in this direction. And that's the key property of a binary search tree. It's not just a family tree with numbers all over the place. They follow a certain pattern. Every element is going to be greater than its left child and less than its right child, assuming you don't have identical values. And that property is actually a recursive one, to borrow terminology from a couple of weeks back. Recall that a recursive function is one that calls itself. A recursive data structure, like the pyramid in Mario, is a data structure that can be defined in terms of itself. Well, a binary search tree is a recursive property insofar as if it applies to this node, it also applies to this node. Case in point, 2 is greater than 1, but it's also less than 3. It's true over here. 6 is greater than 5, but less than 7. And it's technically true of the leaf nodes because the definition is at least not violated there because they don't even have children themselves. So this is a binary search tree because of that pattern. So this then invites the question, well, how long does it take us to search for a value in a binary search tree? Well, if the number is 5, it's going to take me 1, 2 steps. But if there's n elements here, can someone want to generalize that? Either mathematically or just instinctively? Big O of log n. And even if you're not quite sure how the math works out, anytime you take a data set and you have it, we're talking about log base 2 of n again. And indeed, that's going to describe the height of this tree. The height of this tree is essentially log base 2 of n, because if n is 7, it's going to give me essentially 2 when we round appropriately. If we round up, if we've got 8 elements, log base 2 of 8, 2 to the 3rd, so that means 3, so 1, 2, 3. It kind of works out, even if I'm doing that a bit quickly. The height of this tree is log base 2 of n, aka big O of log n. How long does it take to insert? I think it's going to take log n because I can insert over here, or over here, or over here, depending on where the number goes. How long does it take to delete? I'll claim it's going to take about the same. So wow, we're back in business. I've got now the ability to grow and shrink my data structure, because if I want to insert the number 8, it's going to go right there. If I want to insert the number like 5.5, I can see where I would put it. It's going to be easy to add new nodes by just updating the pointers without copying everything in memory like we had to for arrays. But there is a downside here. I got to concede something. What price am I paying? What's the trade-off here? To gain that dynamism and that speed,
Memory.
But yeah, I'm literally using 3 times as much memory now, because even though it's not depicted here explicitly, each of these squares represents an integer and a pointer and another pointer. So that's like 16, that's like 20 bytes at this point of memory instead of just 4 bytes for each of the integers in an array. Nowadays, though, space is pretty cheap. We all have very large Dropbox folders, iCloud folders, and the like, so it's not really a big deal to use that many more bytes. Certainly not a big deal for 7 numbers, but if it's 7 million numbers, maybe this isn't the best data structure to use, even...
What?
My lock.
Oh my god. phone. Oh, it says potential spam. Jesus. God dang it. No. Okay, here we go. Now let me focus. Go get mommy, please. Olivia.
If speed is important, you got to decide ultimately, based on your actual use case, what matters more. So in short, a binary search tree you can kind of think of as an amalgam of, or rather a variant of a linked list, except that every node has as many as 2 pointers instead of 1, which is what gives us now this second dimension. And in fact, this translates pretty nicely to code. In fact, if we consider how we implemented in a linked list a node, recall that it looked like this, where you got a number in each node and a pointer to the next element in the linked list. Well, I think for a binary search tree, we can sort of borrow this as inspiration, make a little more room, because we need 2 pointers instead of 1. And I'm just going to call the left child the left pointer, and the right pointer, but here is the 3 times as much space, give or take, because I now have 3 elements associated, 2 pieces of metadata and 1 piece of data that I actually care about to stitch this thing here together. All right, well, if this is the data structure there, how could I implement this in code? Well, here's where recursion again comes into play. The fact that a binary search tree is recursive in nature, in that what you say about this node, about it being greater than the left child and less than the right child, can be said of this node and this node and this node and this node. You can leverage that beautifully in code like this. So suppose I'm implementing a search function in C whose purpose in life is just to say yes or no, true or false, the number you're looking for is in this tree, which might be a useful thing to check in an algorithm. Search is going to take 2 arguments I propose, the number you're searching for and a pointer to the tree. That is the root of the tree initially. So how do you actually traverse this thing in C code? Well, we can pluck off the easy case first, the base case. If the tree itself is null, like if you hand me nothing, I'll give you your answer right now, false. Like there's no number here if the tree is empty. So that's easy. No! Otherwise, if the number you're looking for is less than the
Olivia, no. I'm not telling you. God dang it. No. You hungry? You want food? You want food? Don't look, your baby movie's on. Baby movie. Look, your baby show. Stop. Look, your baby show's on. So go in there and chill for a second and then start talking shit. Try to I have to eat it. You're just like, I already made it, so I have to eat it now. You're like, this kind of sucks, though. You can throw it out. You don't have to eat it. I swear. Alright. You found me?
Yeah.
Your hands are cold.
What?
Your hands are cold.
No.
Yeah. If true equals no, return
Oh,
false.
Huggy. Huggy.
Go with mommy. Mommy's got crackers.
What?
Mommy's got crackers. Go.
What?
Mommy's got crackers. Go.
What?
Please. You only want in here because I'm trying to study. Whenever I'm out there, you don't even care. Look. Crackers. You want to try some crackers? Have to do what you do.
In the current node. So tree is what's passed in, a pointer to the root.
Mommy.
So if you follow the arrow, you can get inside of that value and see its number. If the number you're looking for is less than that, okay, you want to snip off the right tree and dive down the left subtree. So you search the tree's left child for the same number. Else, if the number you're looking for is greater than that number, you search for the tree's right child for that same number. And the fourth and final scenario is what? Well, if the number you're looking for equals the number in the current node, you got it, return true. And if you recall some of our past design discussions, this is sort of a waste of everyone's time to ask this question explicitly. Let me tighten this up design-wise, because there's only 4 possible scenarios. Either there's nothing there, it's to the left, it's to the right, or you found it. It's right there. So whether or not you agree at this point in your programming career, like there is a beauty to this code that most programmers would claim is here, and that it's so relatively elegant, whereby you've defined what the function is, you've got this base case, which is arguably one of the clunkiest parts, but the fact that you can just check a value here and then traverse the exact same structure, but a subset of it by traversing the left subtree or the right subtree is like a beautiful application of recursion. And it allows you to search for this thing no matter where it is in the computer's memory. Questions then on this idea of a binary search tree or this actual code thereof? Nope, if the number is not there, we recall, so if we get all the...
Here, I want to write this. I thought I gave it an extol. Dang it. Else if hitting too many buttons at the same time. Return, search. Let's return true. Okay. I don't think I can make it. No, okay. Well, I just want to save that, honestly. I'm just trying to save that information. It's just there.
Way to the bottom of the tree, such that now I'm at one of those leaf nodes, and that's not the number I'm looking for, such that there's no left child left, no right child left. This conditional is going to kick in, and I'm going to return false. But if I find it along the way, whether it's at the top of the tree or somewhere in the middle or among the leaves, I will eventually return true. Good question. And to be clear, even though I'm calling this a tree, that's true certainly for the first time I call this function, because I'm passing in a pointer to the whole tree structure. But if you think about it, what's the left subtree and the right subtree? It's just a smaller tree. It's like a baby tree that's attached to this parent node, so to speak. So it's perfectly reasonable to just call the search function with that child, because it in turn has a whole subtree below it, or the right child, which has the whole subtree below it instead. All right, so I like this direction. We've now kind of improved upon linked lists. We've gained back some of our performance because we can now find something with big O of log n time. I don't love the fact that I'm using 3 times as much memory roughly. That feels like kind of a high price to pay just to speed things back up. But let's consider whether or not this thing's actually going to work as the data structure gets bigger and bigger as well. So it looks beautiful here as written, and that's deliberate because I drew the picture like this, and it's got 7 elements in it. But how did we get to 7 elements? Let's start from the beginning. Suppose that the tree is initially empty, and suppose that a human using getInt or some other technique inserts the first element into the list, like the number 2. And the goal is to maintain the binary search tree property, which means you gotta have it greater than left child, less than the right child. So suppose the human using getInt or some other technique next gives me the number 1, no big deal, I plop it right there. Is the left child, suppose they give me the number 3 next, no big deal, it goes right there. I have very deliberately manipulated this story to work out beautifully, such that the tree is smaller, but it's still a binary search tree and nicely balanced, so to speak. But what if the user, for whatever reason, just gives me a more perverse sequence of inputs, like the worst case scenario, to give me 3 elements, and suppose they give me 1 first, okay, that's the root, then they give me 2, okay, that's cool, that's like the right child, but what if they then give me 3? Well, to maintain that binary search property, the 3 has to go over here. Suppose perversely then they didn't give me 4, then 5, then 6. Imagine in your mind's eye where this story is going. What have I accidentally created in memory then? A linked list, which is like bad for all the reasons we discussed before the break, because even though we're getting the dynamism, it's devolving into big O of n. So I've kind of manipulated the situation here with their original example with 7 elements and then 3 elements by making sure that they were inserted in just the right order. Because unless you are clever about how you build the tree in memory, it could very well devolve from a tree in 2 dimensions into actually a linked list in one dimension. And now this is just a long and stringy tree that does not violate the binary search tree definition, but it is surely not balanced in this case. Now, as an aside, if you take higher level languages and data structures and algorithms, there's many different alternatives to binary search trees that actually have baked into the algorithms a little bit of rejiggering of the structure so that really, as soon as you insert this 3, you spend a little bit more time and clean the situation up. And essentially what you do is like pivot the thing around this way so that 2 becomes the new root, and then 1 hangs off of it, and 3 still hangs off of it. So with each insertion or deletion, you rebalance the tree as needed, which does cost you a bit more time, but it avoids the thing devolving into big O of n again. And we won't do that in code, so this is recoverable, but not if you implement it naively, as I did, at least verbally, in this story. All right, well, can we do better than that? Well, why might we want to? Well, at this point in the story, it certainly could devolve into big O of n, and that's not great, certainly for large data sets. It's nice that we're back to log n, at least if you take on faith that we could kind of rebalance this thing as needed and maintain a logarithmic height for it. But really, the holy grail of data structures is to achieve something that is big O of 1, like constant time, whereby no matter how many numbers or names or sweaters are in the data structure, it will take just 1 step, or maybe 3 steps, or heck, even 100 steps, but a number of steps that is completely independent of how many actual pieces of data are in the data structure. That is to say, over time, it doesn't get any slower, even if you've got tens, hundreds, thousands, millions of elements in there already. So how do we gain something like big O of 1, constant time, the appeal of which is reminiscent of our early picture from week 1. Like, this was our early algorithm for finding someone in a phone book or counting students in the room, something linear, literally straight lines. This was the logarithmic curve, which, especially as you zoom out, starts to get very, very appealing time-wise. Something that's constant time looks even prettier. It is a straight line at like the 1-step mark or the 2-step marks, whatever the constant number of step marks is. And even though logarithmic will still grow in perpetuity, constant time, by definition, never changes. And this is what we'd really like. So when you're searching for someone in your phone, you're searching for something on Google, you're asking a question of ChatGPT, you get an answer like that in constant time, independent of how much data is actually in there. Well, let's see how we can do this. To do this, we're going to at least need a new building block, a term of art known as hashing. Hashing sort of formally takes an infinite domain of values and maps it to a finite range of values. So from high school math class, domain is the input, range is the output. So an infinite domain to a finite range is the goal here of hashing. And we might see this actually in the real world when you're playing, games or whatnot, or you're cleaning up after a game. Like here are some super jumbo playing cards that we got online. And suppose that you want to just get these into sorted order. You could do this very painstakingly. There's 52 cards here. You can kind of lay them all out and start sifting through them and put the 2 over here and the 4 over here and the hearts and the clubs and so forth. Or you can start to look at the cards and bucketize them first to take a 52 size problem and maybe shrink it down into 4 13-byte problems. So here, for instance, is where the first diamond might go, the club here, spade over here, diamond over here. And I can kind of just do this again and again, bucketizing, literally, all of these values so that I've got a very simple heuristic that allows me to move the cards into these buckets, each of which is going to have a subset of the values, and then I've got smaller problems I can deal with. So ... assume that I bucketize all 52 of these values, then I've just got 4 problems remaining, and I dare say it's a little easier then because they're all of the same suit, and so I can pretty easily sort it from ace to king or whatnot, because those are effectively just numbers at that point. So hashing refers to, again, taking values from an infinite range. In this case, it can be finite, and it is in this case, but if you were doing it more generally with numbers, you just have to map it to a finite range, like 1, 2, 3, 4, finite number of buckets of values, at which point then you can solve the problem a little differently, or a little more efficiently. So why is this germane? Well, I would propose that if we want to start organizing our data in memory, Toward an idealistic goal of achieving constant time, hashing might be one ingredient for the solution there too. And generally, we're going to describe the process by which you decide what input goes to what output is namely what's called a hash function. It's a mathematical function or a function in code that takes as input a card from a deck or maybe a word from a dictionary and outputs a value that represents the bucket into which it should go. So in the case of our contacts app, for instance, of course, in the GUI of it, you have all of your friends and family top to bottom, alphabetically, presumably. You might want to ideally find someone quite quickly, ideally in constant time, right? The naive implementation that Apple or Google could implement is just use linear search. Search through all of your contacts, top to bottom, and eventually you will correctly find the person. But wouldn't it be nice if they instead use an array and then they can use binary search and get you the person in logarithmic time? That's great, but if you have a lot of friends and family in there or a much larger data set, wouldn't it be nice to just jump to the answer in one step instead of even log of n steps? So that's our goal. Can we get close to or actually at constant time? So with the hash function, we essentially have our old friend problem solving here, the inside of which the algorithm is known as a hash function. And for instance, if I'm looking up Mario's number, I might now want to look for Mario, not top to bottom, or not divide and conquer, jumping around to the middle of the middle of the middle. Let me just figure out what bucket Mario is in. And in the English alphabet, there's 26 letters of the alphabet, A through Z, either uppercase or lowercase. And suppose that I want to find what bucket Mario is in. Well, much like these cards and the suits thereof, wouldn't it make sense that anyone whose name starts with A goes into the first bucket, and maybe the B's go into the second bucket, and the ... Z's go into the last bucket? So it stands to reason that if I pass in Mario to a hash function implemented in C or some other language, I would like to get back the number 12, because M is the 13th letter of the alphabet, but if we start counting at 0 with our buckets, which are essentially an array, then it's index location 12 instead of 13. Similarly, if Luigi is the input, I'd like to get back the number 11. So my hash function somehow takes as input in this story a string and gives me an integer. I claim there's theoretically an infinite number of names in the world in the English language, but there's only going to be 26 possible answers from this hash function, 0 through 25, so that's our infinite domain to our finite range. Instead of 4, it's now 26. All right, so what should we do with the computer's memory to leverage the fact that we can very easily bucketize names based on the first letter of someone's name? Well, let me propose that the hash function part of this, arcane as it looks, is actually pretty straightforward. So if you wanted to translate this idea into C, you can include ctype.h, which we've used a few times to get at access to like functions like toUpper, and this is just to make sure you can be case insensitive. Here's my hash function. It's going to return an int, which is the goal. Takes a string as input. We'll call it name. And what does this function do? Well, it's kind of some clever ASCII arithmetic. It first converts to uppercase the first letter of that person's name. So if it's in all lowercase, forces it to uppercase. Why? Because I want to subtract no matter what 65, aka the ASCII value of capital A from this, and I don't want to screw up the math if I'm doing like a lowercase letter minus a capital. I want capital minus capital is all. So this will return to me a number between 0 and 25 inclusive, because if it is a name that starts with A, I'm only looking at the first letter. I'm subtracting off A, that gives me 0. And I'm going to return 0 as a result. ... If it's Z, I'm going to return 25 instead. Now, there's no error checking in here. If you type in non-English symbols, it's going to break. So let's just assume for simplicity this is indeed an English name that's coming in. I can refine this a little bit. I'm going to propose moving forward in our final week here of C, there are some added defenses you can put in place when writing code. Like if you know that you're receiving a name as input, that is, you're passing something in by reference, there's a danger now, per last week, because now the caller of this function, whoever's...
Dang, I gotta pee again. Oh my god. Ah, that coffee ain't working with the crap.
using this function is telling you where to find Mario and where to find Luigi's name. The problem with that is that you could go to that address and actually change their name in memory, even if you're not supposed to. You're supposed to just use the name. So you can do something like const, which says you should not be able to change this value, even though I'm not giving you a copy of it by value, I'm giving you a reference there too. Another refinement here is that a hash function for an array as the goal should return a value that's 0 or 1 or 2 on up, never negative. So we can even more protectively say it's not just an int, it's an unsigned int. And we talked briefly about that last week, albeit in the context of chars. These are just like minor improvements that makes your code arguably better designed because you're opening yourself up to fewer possible mistakes or issues. All right, so with that said, let's now assume that we've got this kind of function implemented, and we can now use it to decide what bucket to put these people's names into. Well, let's give you what are called hash tables, which are sort of the Swiss Army knives of data structures, the kind of thing that some computer scientists have been quoted as saying if they were stuck on a desert island with only one data structure, this is probably the one they would want. Why? It's just really generally useful because it allows you quite powerfully to associate keys with values, which is to say, to come full circle today, hash tables are often how you would implement at a lower level the thing we began class with, talking about dictionaries, collections of key value pairs. That, after all, is what a phone book is. We call it, names and numbers, but it's keys and values. That's what an actual English dictionary is. The Oxford English Dictionary, it's a bunch of words and definitions or keys and values. So useful in general to be able to associate one piece of data with another, ergo hash tables. So here's how you might implement in C a hash table. You want it to be of size 26, for instance, so 26 buckets from A to Z, hence the 26. You want this to be an array, and that's fine. This is an array of 4 buckets. I'm going to use an array of 26 buckets because a hash table 2 is going to be an evolution of our linked list mashed together with an array. So a hash table, in short, is going to be an array with linked lists, as we'll soon see. Here's the array, 26 pointers to nodes. So I'm going to give myself an array of pointers that is going to store, ultimately, a whole bunch of person objects like this. So for instance, here's a char star name, char star number, as we've discussed in the past, representing a person. These are the pieces.
I need something.
Of data I might want to store in this data structure. However, let's simplify it. Let's not worry about the phone number because we're not going to call anyone today. But for a linked list of persons, I'm going to need to store, let's say, the person's name, but also a pointer to the next such name, to the next such name, to the next such name. So again, I'm just deleting number as being unnecessary detail. But if we're going to have an array of linked lists, this is our new definition of node for this part of class, whereby it's not for a tree, it's now for a hash table. And we'll see this in action now. Here's my array of size 26. I drew it vertically, but who cares? These have always been artist renditions thereof. It just fits nicely on the screen this way. This is location 0, this is location 25. So any A names should end up over here, any Z names should end up down here, and so forth. Let's just generalize this away as letters of the alphabet for clarity. That's where all of the names are going to go. So hopefully Mario here, Luigi here, and everyone else. So what are each of these squares? They're just pointers to nodes. Initially all null, all claimed, but as soon as I insert Mario into this so-called hash table, I'm not going to put him literally here. I'm going to create a new node in memory, put Mario there, and then stitch it together. Because if I get another M name, I'm going to stitch it together and together and together again. So for instance, here comes Mario into this data structure. So this is a pointer to a person structure. Here's Luigi, and here's a third character as well, Peach. That's all working out great. Dot, dot, dot. There's a whole bunch of characters in the Nintendo universe. Here's a lot of them. Unfortunately, especially if you're a fan, there's also other names that do start with M and L and other letters of the alphabet, so we're poised to have what we're going to call collisions, which is a downside of using a hash function. If you're going from something infinite to something finite, by definition, you're going to have a heck of a lot of potential collisions somehow. Multiple M names, multiple L names, and so forth. So we've got to mitigate this somehow. Well, if you meet someone in the real world whose name happens to start with M and you already are friends with Mario, well, you could delete Mario from your phone and put that new person there, but that's kind of dumb. You could clobber the value, that is. Or maybe you put the M friend here, and when that fills up, you put the M friend here, and then when you meet someone else whose name starts with M, you put it here. But then it just devolves into this mess, at which point now there's no rhyme or reason as to who is where. It devolves back into something linear. If you have to search the whole darn thing looking for M friends just because you ran out of space where you want it. So here's the beauty of mashing together an array with a linked list. You hash the name to the intended location, like box 12 here, and then you just start stringing them together in a linked list. And hopefully you don't have too many of those collisions, but at least now you don't have to delete or make a mess of the data structure. So here's another bunch of names, 3 starting with L. Here's a bunch for the other letters of the alphabet. And it's just it's an array now of linked lists. This then is a hash table. So the question to consider now, is this better than an array? Is this better than a linked list? Well, I dare say it's better than a linked list, because if it were a linked list from A to Z, what would be the running time of searching for anyone? Well, I'll spoil it, big O of n, because even if it's alphabetically sorted, you got to start at the beginning and go all the way through the list potentially to find someone like Zelda whose name starts with, of course, Z. But here we have an array of linked lists, so what's really the running time here? It's not quite as bad as n steps, because if you assume a uniform distribution of names such that the world of Nintendo maybe has as many M names, as L names, as A names, as B names, you could assume that there's a bunch of chains, a bunch of linked lists here chained together, but they're all roughly the same. So maybe you have N names in your phone book this way, but these lists are only of size, they're only 1/26 of that length, because you've got that many names there. So what's the running time? Well, ideally, we'd move away from linked lists with big O of n and achieve our constant time, but we have these collisions to worry about here. Just to be clear, we want to get from big O of n to something constant time, but we're not going to get to constant time if we've got collisions. If we've got 3 L names and a few B names and a few A names, we can't just jump to that location and find the person we're looking for. So what's the fundamental goal? Well, I think we want to maybe use a smarter hash function. And here depicted is an excerpt from a bigger hash table that is a much bigger array that assumes that you're not looking at the first letter of everyone's name, but apparently what instead?
The first 3 letters?
The first 3 letters of the person's name, which just decreases the probability of collisions, because in this model, I dare say there's no one else's name in the Nintendo universe that starts with L-I-N, so now Link has its own location in memory, and similarly for Luigi, L-U-I, I believe is unique in the Nintendo universe, so we don't have a collision. Unfortunately, while this does seem to eliminate collisions, based on this tiny example, what's the trade-off? Or what's the catch? Yeah.
I'm gonna slow it down.
This is a lot more memory. I mean, kind of hinted at the fact that I didn't even fit most of it on the screen anymore. Here's L-A-A, here's L-U-G, but what about all of the other letters of the alphabet and the other combinations of ... all possibilities. Moreover, some of these just don't make much sense, at least in English or in the Nintendo world. I don't think there's anyone whose name is going to start with AAA, or AAB, or AAC, or AAD, or AA, and so forth. We're wasting a huge amount of space to reduce the probability of collisions. So that's fine. We might get constant time now, but at what cost? Well, a heck of a lot more memory. And so this is one of the tensions when using a hash table, is you want to come up with a good hash function that's maybe a little more sophisticated than the first letter, but not so wasteful that you need a crazy number of buckets and therefore a huge amount more memory. So really, even with collisions, it's not quite as bad as n steps, because technically if you have k buckets, where k is like 26 buckets, or 4 in this case, technically if you do assume that the names are uniformly distributed over A through Z, the English alphabet, well, each of those linked lists is going to be hopefully no bigger than n divided by k, so n divided by 26. But what do we know about higher order terms when doing big O notation? Big O of n divided by k, yes, it's faster, but asymptotically, that is theoretically, you're still talking about big O of n. So here's attention though, like it's absolutely going to be faster. It will be like 26 times faster than a linked list, but it's still just big O of n because it's going to take an amount of time that's still linear in the size of the data set. So we seem to have strayed yet again away from our constant time search. So can we find this holy grail? Well, we kind of can if you let me spend just like a lot more space. There are tries in the world, which weirdly is short for retrieval, even though we don't say retrieval, but a trie is a tree made out of arrays. Right? So at some point, computer scientists were just like mashing things together Frankenstein style, like linked lists and arrays, and now we've got trees and arrays. You two can mash something together and come up with your own, but let's look at what a trie actually is, because it is going to get us that constant time grail. So here is the root of a trie. You can think of each node in a trie as really being an array of values, A through Z in the case of an English problem like we've been playing with here. And what you do is you treat this array as being indexed from 0 through 25, or equivalently A through Z, and you treat each of those elements as a pointer to another such node in the trie. And what you do is implicitly store the names that you're storing in this data structure by going to an appropriate location based on the first letter in their name, and then adding a pointer that represents the second letter in their name, adding a pointer that represents the third letter of their name, and so forth. So what do I mean by this? Suppose we want to insert Toad, one of the characters in the Nintendo universe first. If we count up where T is in the alphabet, this pointer here will be changed from null to a pointer to a new node that represents the second letter in Toad's name, which is going to be, of course, O. Then to insert TOA, we're going to need another node. A is going to lead me to D, and for depiction's sake, I'm going to draw it in green, even though this would actually be a Boolean or something like that in memory that indicates that Toad's name stops here. So in other words, this trie in memory has 4 nodes now. Each of those nodes is essentially an array of size 26, but the word Toad is not actually stored in the data structure explicitly. There's no char star Toad, but implicitly, because the T pointer is non-null, the O pointer is non-null, the A pointer is non-null, and the D pointer is in fact null at this point, is the common technique here. This allows me to insert other names from Nintendo's universe, like Toadette, because I can continue from here to go to the E node, to the T node, to the T node again, and an E node, which I'll again mark in green. So you can even have names that are substrings, or equivalently superstrings of each other, by just having all of these various breadcrumbs along the way, where again, a non-null pointer here to a non-null to a non-null to a null pointer here indicates that, or it can't be null at this point, this is where we have to use a Boolean, indicates that there is a name in this data structure that ends here, and there's another name that ends here. Meanwhile, if there's a third name from the universe like Tom, same idea, but eventually we can start reusing some of these arrays whereby non-null, non-null, null, or there's a Boolean flag here that says true, a name ends here, now we're reusing that same array. So each of the nodes represents the ith letter of the word or the name you're trying to store in the data structure. And by playing around with null and non-null and some Booleans, you can implicitly store names in this structure. Now, it's way too pictorially difficult to depict lots and lots of names in this form. So just imagine in your mind's eye that there's dozens, hundreds, thousands of names now in this data structure with just more arrows and more arrays. How do you actually look someone up in this data structure? Well, if you want to ask a question like, is Toad in this data structure, or is Toadette in this data structure, or anyone else, you can simply start at the root node, as we would do for any tree, and you hash on the first letter of Toad's name, which gives you this location, and you check, is it null? If not, T is implicitly there, so you follow that pointer here. And then you hash the second letter of Toad's name, an O, and check this pointer, and you follow that arrow. Then you check the third, you hash on the third letter of Toad's name, A, and you follow that arrow. Then the fourth letter of Toad's name, D, and you see, there's a Boolean here, represented in green, that means Toad is in this data structure. And notice what's subtle here. It doesn't matter if there's 3 names in this trie or 3 million names in this trie. How many steps did it take me to confirm or deny that Toad is in this trie? 1, 2, 3, 4, which is arguably constant, even though the names can vary. At some point, there's no Nintendo name longer than what, like 10 characters, 20 characters, maybe 30. I mean, there's some reasonable bound that is finite where there's never going to be a name longer than that because Nintendo's never going to come up with a crazy long name for a game. And so you effectively have constant time for looking up T-O-A-D, Toadette, Tom, Mario, Luigi, Peach, any of the other names we've looked at. So this is to say, a try allows you to ask questions like, is Toad in this data set? Or equivalently, what is Toad's phone number in this data set? Because if you assume now that each of these pointers ultimately is not just a bool saying yes or no, but maybe it's an actual person structure with a name and a number, you can store even data like that. Your key value pairs where your names are your keys and your phone numbers are your values. To make this more clear, then here is a data structure how we might represent in C each of these nodes. It's not quite technically just an array. It's an array of size 26. We'll call it children because it represents the children of that node of type struct node star. And then here, for instance, for simplicity, is that person's number if we reintroduce numbers and want to store in this data structure someone's phone number as well. So using that data structure and that kind of code, you can implement a try using something as simple as this. Initially, your try is just a pointer to a node, one such struct. We can, of course, initialize it to null to make clear that there's no names in here. But each time we allocate a node, we can then add another node, hashing on the first, the second, the third, the fourth, the last character in the person's name, allocating a node as needed, flipping that Boolean to true or false, or adding their phone number as a char star to indicate that we have then found them. And so of all of the data structures we've looked at today, big O of 1 is actually achieved with tries. And yet, curiously, for problem set 5, you're not going to implement tries, you're going to implement hash tables. That sort of Swiss Army knife of data structures that like every programmer everywhere knows about. Why? Like, why not use tries very often in practice, perhaps?
Memory.
Certainly can, but what's the trade-off, perhaps?
Memory?
Yeah. It's a huge amount of memory.
Yeah.
Things have escalated since the start of class. We started with one int, then we added an int and a pointer, an int and 2 pointers. Now I'm proposing 26 pointers plus a Boolean or a data structure called person. I mean, it's escalating significantly. And the biggest catch with a try, as you might have imagined with Toad and Toadette and Tom on the screen, there's a huge amount of wasted memory. Just as we saw with a hash function potentially, but that can be reined in as you'll explore in the problem set with a try. Most of the pointers in those arrays are just null and unused. And it just tends to result in you using way more memory to solve the problem correctly, but in a way that tends to slow the computer down and just waste more memory than is useful. That said, just as we started today, there are stacks in the real world, there's queues in the real world, there are even hash tables in the real world, which you'll indeed implement in code for problem set 5. Has anyone here ever had a salad from a restaurant called Sweet Green in Harvard Square? Also elsewhere in the US, like no, one, two, like 2 of us, 3 of us? Okay, so not hard to imagine going to such a store, getting in a queue, and staring at a shelf like this, because what Sweet Green and similar restaurants do when you order for pickup is they hash your salad into a shelf like this. And so literally in Sweet Green, you'll see some wooden shelves like this. This is the A through E bucket, the F through J bucket, the K through N bucket, and the O through Z bucket, whereby if your name, like Malin, happens to be in one of those ranges, they will hash my salad and put it here. But of course, even in the real world, there are some constraints. And what can go wrong with this here hash table system? Someone who's been there, maybe. What can go wrong? Imagine like the extreme, lots of values here, yeah. So there's no more space, right? So, and this has happened to me in the past, especially since Sweet Green, before adopting this system, they used to put the A's here, the B's here, the C's here, the D's here, and so forth. And then someone at some point realized that they were very frequently overflowing the A's to the B's and the B's to the C's. That no one was using Q or Z with any frequency. And so they were sort of wasting space and running out of space. So at some point they decided to like literally remove most of the letters of the alphabet, make the buckets bigger and fewer. So now it's very unlikely that you're going to have so many K's through N's that you overflow the shelf, but this is in the real world a data structure like we've seen today. And so therefore among the goals, even as arcane as things seem to be getting with all the pointer notation and dereferencing this and that, really all we're doing in code is implementing real world solutions that other people have already come up with and translating them to a new domain. And the very last thing you'll do in C this week is indeed implement your very own spell checker, whereby we'll give you a very large file of 100,000 plus English words. You'll have to come up with a clever and efficient way to load it up into memory, and we'll give you tools that will actually measure how fast or how slow your code is, how much memory or how little memory your code is, so as to actually compare it against not just your own, but perhaps others as well. So with that said, we'll end a bit early today. We'll see you next time.
Ooh, that was a lot. Finish the lecture. I gotta do the problem sets. What are you doing? What is that? Correctly. They're like,
The
what,
whole purpose is
what does that take?
do whatever it takes.
You got a lot. I did it a lot of times. When is it enough?
Call up my side piece again.
I'm fucking tired right now. I'm trying to.
Tell us, I was like, bro, you got a camper. We could just make it to where we could just meet him in the backyard car real quick. What's up? Not opposed to it. Get real dirty.
Oh no, dude.
You could just be peeking in the window. What y'all doing out here? Don't mind me. Breathing on the window.
Oh, what is it, Olivia? You're all done? You said you didn't want no crackers. Oh. You said you didn't want any crackers. There we go. Time to do the problem sets. Alright. Oh man, that was a lot. That was a lot. I don't know. Let's see what I can do with it. What the heck?
It's often said that despite humanity's many conflicts, we all bleed the same blood. It's a nice thought, but not quite accurate. In fact, our blood comes in a few different varieties. Our red blood cells contain a protein called hemoglobin that binds to oxygen, allowing the cells to transport it throughout the body. But they also have another kind of complex protein on the outside of the cell membrane. These proteins, known as antigens, communicate with white blood cells, immune cells that protect against infection. Antigens serve as identifying markers. allowing the immune system to recognize your body's own cells without attacking them as foreign bodies. The two main kinds of antigens, A and B, determine your blood type. But how do we get 4 blood types from only 2 antigens? Well, the antigens are coded for by 3 different alleles, varieties of a particular gene. While the A and B alleles code for A and B antigens, the O allele codes for neither. And because we inherit 1 copy of each gene from each parent, every individual has 2 alleles determining blood type. When these happen to be different, one overrides the other, depending on their relative dominance. For blood types, the A and B alleles are both dominant, while O is recessive. So A and A gives you type A blood, while B and B gives you type B. If you inherit one of each, the resulting codominance will produce both A and B antigens, which is type AB. The O allele is recessive, so either of the others will override it when they're paired, resulting in either type A or type B. But if you happen to inherit 2 O's, instructions will be expressed that make blood cells without the A or the B antigen. Because of these interactions, knowing both parents' blood types lets us predict the relative probability of their children's blood types. Why do blood types matter? For blood transfusions, finding the correct one is a matter of life and death. If someone with type A blood is given type B blood, or vice versa, their antibodies will reject the foreign antigens and attack them, potentially causing the transfused blood to clot. But because people with type AB blood produce both A and B antigens, they don't make antibodies against them, so they will recognize either as safe, making them universal recipients. On the other hand, people with blood type O do not produce either
Can only take
antigen,
O.
which makes them universal donors, but will cause their immune system to make antibodies that reject any other blood type. Unfortunately, matching donors and recipients is a bit more complicated due to additional antigen systems, particularly Rh factor, named after the rhesus monkeys in which it was first isolated. Rh plus or Rh minus refers to the presence or absence of the D antigen of the Rh blood group system. And in addition to impeding some blood transfusions, it can cause severe complications in pregnancy. If an Rh negative mother is carrying an Rh positive child, her body will produce Rh antibodies that may cross the placenta and attack the fetus, a condition known as hemolytic disease of the newborn. Some cultures believe blood type to be associated with personality, though this is not supported by science. And though the proportions of different blood types vary between human populations, scientists aren't sure why they evolved, perhaps as protection against blood-borne diseases, or due to random genetic drift. Finally, different species have different sets of antigens. In fact, the 4 main blood types shared by us apes seem paltry in comparison to the 13 types found in dogs.
Well, that was interesting. A person's blood type is determined by 2 alleles, different forms of gene. The 3 possible alleles are A, B, and O, of which each person has. And you know what? I don't need to read this.
A person's blood type is determined by 2 alleles, i.e., different forms of a gene. The 3 possible alleles are A, B, and O, of which each person has 2, possibly the same, possibly different. Each of a child's parents randomly passes one of their 2 blood type alleles to their child. The possible blood type combinations, then, are OO, OA, OB, AO, AA, ABO, BA, and BB. For example, if one parent has blood type AO and the other parent has blood type BB, then the child's possible blood types would be AB and OB, depending on which allele is received from each parent. Similarly, if one parent has blood type AO and the other OB, then the child's possible blood types would be AO, OB, AB, and OO. In a file called inheritance.c in a folder called inheritance, simulate the inheritance of blood types for each member of a family.
Is there a way to...
You ain't taking food over there. You can eat it over here.
Proofread? I just wanted to read it. Crap, I'm not asking you. I just want to...
Hi, glad to meet you. I think we're going to do great work together. Where shall we start?
I don't know. This other voice thing kind of sucks, though. I can't choose like a different voice. Manage extension. Options. Voice. Premium voices require purchase. Experimental AI voices. I just want it to not sound so awful. Let's see.
A person's blood type is determined by two alleles,
Rough.
i.e., different forms of a gene. The three possible alleles are A, B, and O, of which each person has two, possibly the same, possibly different. Each of it.
Hold on a second.
Read Aloud is a Chrome and Firefox extension that uses text.
Read Aloud is a Chrome and Firefox extension that uses text.
Read Aloud is a Chrome and Firefox extension. Read Aloud is a Chrome and Firefox extension that uses text-to-speech technology to convert web page text to audio. It works on a variety of websites, including news sites, blogs, fan fiction, publications, textbooks, school and course materials.
I'm trying to pay for them.
Read Aloud is a Chrome and Firefox extension that uses text-to-speech technology to convert web page text.
Read Aloud is a Chrome and Firefox
Alright, that sounds
extension
better.
that uses text-to-speech technology to convert web page text to audio.
I'm so robotic.
It works on a variety of websites, including news sites, blogs, fan fiction, publications, textbooks, school and course materials.
Alright, I think we can do it now. Let's try this.
A person's blood type is determined by two alleles, i.e., different forms of a gene. The three possible alleles are A, B, and O, of which each person has two, possibly the same, possibly different. Each of a child's parents randomly passes one of their two blood type alleles to their child. The possible blood type combinations, then, are OO, OO, OB, AO, AA, AB, BO, BA, and BB. For example, if one parent has blood type O and the other parent has blood type BB, then the child's possible blood types would be AB and OB, depending on which allele is received from each parent. Similarly, if one parent has blood type O and the other O, then the child's possible blood types would be O, OB, AB, and U. In a file called inheritance, see in a folder called inheritance, simulate the inheritance of blood types for each member of a family.
Download the distribution code. wget. What's up? TTP. Else. Not found. And Jared. Oh man, God, all that typing. CS50.net. 2026. XP sets. Inheritance. Oh crap. Zip. Okay. Zip. Inheritance. Ah crap. Zip. Cannot remove it. Oh. Zip. Alright, it's there. Alright. Complete the implementation. Blah, blah, blah.
Complete the implementation of inheritance. C, such that it creates a family of a specified generation size and assigns blood type alleles to each family member. The oldest generation will have alleles assigned randomly to them. The create_family function takes an integer, generations, as input and should allocate, as via malloc, one person for each member of the family of that number of generations, returning a pointer to the person in the youngest generation. For example, create_family 3 should return a pointer to a person with two parents, where each parent also has two parents. Each person should have alleles assigned to them. The oldest generation should have alleles randomly chosen, as by calling the random_allele function, and younger generations should inherit one allele, chosen at random, from each parent. Each person should have parents assigned to them. The oldest generation should have both parents set to null, and younger generations should have parents be an array of two pointers, each pointing to a different parent. Take a look at the distribution code in inheritance. C. Notice the definition of a type called person. Each person has an array of 2 parents, each of which is a pointer to another person's struct. Each person also has an array of 2 alleles, each of which is a char, either A, B, or O.
But just is a one?
Okay, makes sense.
Now, take a look at the main function. The function begins by seeding, i.e., providing some initial input to a random number generator, which we'll use later to generate random alleles.
Random number generator.
The main function then calls the create_family function to simulate the creation of person structs for a family of 3 generations, i.e. a person, their parents, and their grandparents. We then call print_family to print out each of those family members and their blood types.
Okay. Well, the P is the pointer to the person. Okay. Print family tree of blood types. Okay. A person, which is the P is pointing to person, and the person has what, 2 arrays of 2 parents and 2 alleles. That's free memory.
Finally, the function calls free_family to free any memory that was previously allocated with malloc.
Oh, create family. Okay.
The create_family function should return a pointer to a person who has inherited their blood type from the number of generations given as input. Notice first that this problem poses a good opportunity for recursion. To determine the present person's blood type, you need to first determine their parents' blood types. To determine those parents' blood types, you must first determine their parents' blood types. And so on until you reach the last generation you wish to simulate. To solve this problem, you'll find several to-dos in the distribution code. First, you should allocate memory for a new person. Recall that you can use malloc to allocate memory and size of person to get the number of bytes to allocate.
Now we're creating size. Allocating memory for a new person. So I'm creating Holy crap. Creating memory for a new person. A person is a structure that's defined by the parents and the alleles.
Is that this?
Families with them. Great family. Wow. I'll do with the book. No, there it is. I need a better pen than this. Maybe use a pencil. So here we have and this is pointing to person. And a person is defined as
No matter how much I try to make my hair look normal,
mm-hmm.
the color still wants to shine through.
The color still wants to what?
Shine through.
Shine through.
Mm-hmm. All that beautiful dark burgundy fell out on the bottom, and that blue's still trying to come through.
Oh, yeah.
I want to go back to turquoise, but I really want an office job that pays good.
Oh.
And especially since I know how to turn an interview process around to where I'm interviewing them.
Hey, what type of blood type you say you have?
I think O positive.
O positive?
Mm-hmm.
So OO?
It's magic, you know.
So I wasn't trying to sing a song. Well, because this doesn't have anything to do with coding, but it just told me a bunch of stuff about blood, blood types.
TED Ed. Is it
Well,
educational
because
TED Talk?
it's yeah, but it's part of the coding thing. I'm using coding with testing blood types. As if you have A, B, you can accept any blood type. If you have A, you can accept A. If you have B, you can accept B. You have two alleles. However you say that.
I can give anybody my blood, but I can't receive anyone's blood. I have that blood type.
You can give anyone.
Yeah, when I went to get all my stuff done, they said I have the blood type that I could donate to everybody, but I can't get everyone's blood. So whatever blood type that is.
Oh, I don't know. That's not a type.
I think it is.
That I know. That's not what it. It was saying, well, if you have A, B, you can receive any blood type.
Mm.
But if you have O, then you can only receive O. And if you're A, you can only receive A. And if you're B, you can only receive A. But they didn't say if...
There's a blood type that's universal that can give out blood, but can't get they have to get that specific kind of
Well,
blood.
but maybe it is the double O, because they didn't say that, but like, they said if you have AB blood type, you can take any blood type. But if you have A type, you can only take A. If you have B, you can only take B. But O is the absence of A and B. So maybe that's what it is. If you have O type, so you can only have O type blood, but you can probably give it to anybody because the white cells won't reject it because it's not A or B. But
What are you?
It's often said that despite humanity's many conflicts,
Oh
I don't even know how you find out. Like,
same
just
blood. It's
well,
a nice
I
thought,
tried donating
but
plasma
not
once
quite
and then it almost
accurate.
killed me. So.
In fact, our blood comes in a few different varieties. Our red blood cells contain a protein called hemoglobin that binds to oxygen, allowing the cells to transport it throughout the body. But they also have another kind of complex protein on the outside of the cell membrane. These proteins, known as antigens, communicate with white blood cells, immune cells that protect against infection. Antigens serve as identifying markers, allowing the immune system to recognize your body's own cells without attacking them as foreign bodies. The two main kinds of antigens, A and B, determine your blood type. But how do we get 4 blood types from only 2 antigens? Well, the antigens are coded for by 3 different alleles, varieties of a particular gene. While the A and B alleles code for A and B antigens, the O allele codes for neither. And because we inherit one copy of each gene from each parent, every individual has 2 alleles determining blood type. When these happen to be different, one overrides the other, depending on their relative dominance. For blood types, the A and B alleles are both dominant, while O is recessive. So A and A gives you type A blood, while B and B gives you type B. If you inherit one of each, the resulting codominance will produce both A and B antigens, which is type AB. The O allele is recessive, so either of the others will override it when they're paired, resulting in either type A or type B. But if you happen to inherit 2 O's, instructions will be expressed that make blood cells without the A or the B antigen. Because of these interactions, knowing both parents' blood types lets us predict the relative probability of their children's blood types. Why do blood types matter? For blood transfusions, finding the correct one is a matter of life and death. If someone with type A blood is given type B blood, or vice versa, their antibodies will reject the foreign antigens and attack them, potentially causing the transfused blood to clot. But because people with type AB blood produce both A and B antigens, they don't make antibodies against them, so they will recognize either as safe, making them universal recipients. On the other hand, people with blood type O do not produce either antigen, which makes them universal donors, but will cause their immune system to make antibodies that reject any other blood type.
Yeah, that's what you are.
Matching donors and recipients is a bit more complicated due to additional antigen systems, particularly the Rh factor, named after the rhesus
Well,
monkeys
according to this,
in which
that's
it
the
was
most
first
common
isolated.
one.
Rh
And the
plus
rare
or
one is the
Rh
AB.
minus refers to the presence or absence of the D antigen of the Rh blood group system. And in addition to impeding some
keeps
blood
giving me
transfusions,
crackers.
it can cause severe complications in pregnancy.
There's a snack.
If an Rh negative mother is carrying an Rh positive child, her body will produce Rh antibodies that may cross the placenta and attack the fetus, a condition known as hemolytic disease of the newborn.
Pick it up.
Some cultures
Pick it
believe
up.
blood type to be associated with personality, though this is
Okay,
not
still gotta
supported
pick
by
it up.
science. And though the
Throw it away.
proportions of different blood types
Throw it
vary
away.
between human populations,
you.
scientists aren't sure why they evolved. Perhaps as protection against blood-borne diseases, or due to random
No,
genetic
look,
drift.
it's the Hispanic part of me.
Finally, different species have different sets of antigens. In fact, the 4 main blood types shared by us apes seem paltry in comparison to the 13 types found in dogs.
No, that's what you are.
Blood type?
Yeah.
You're a blood type. Your
But
mom's a blood type.
Did you see how common it is, though?
Yeah.
Diseases.
It's like the O one's the most common one, the AB one's the most uncommon.
But they can't give out to anybody. They can only give out to themselves. See, I could give out to
Yeah.
everybody.
Yeah, so it's common, but it's not, I guess.
Universally able to accept blood.
Yeah. Why?
Because I love you.
Because you love me? Doesn't make no sense.
No more crackers. We're done.
Okay. Anyways.
Thank you. You're giving me all the crackers.
Let me get back to where I was. Okay, wait. Oh, that's what I was doing. Okay, so I got. So create family. What is your creating family? And P is a string that sends you to persons, or a pointer that sends you to person. Create family is a pointer that sends you to person. So you got 2 pointers sending you to person, but then parents also sends to person. There's so many pointers that go to person. Let's see, P also goes to person, apparently. I got everybody pointing to this one person.
I'll point at something.
No, person also comes with the integer of generation. Generation is a constant of 3. And then what's indent length? Indent length. I don't know what that is. Okay. So create a new film. Okay, so first, seed random number generator. Okay. Create a new family with the 3 generations. Okay, so we just created, what, 3 people? Or 3 generations. Create a new family with 3 generations. Okay, so we did this. What are you doing? Oh, Jesus.
You were basically zombie.
With 3 generations, which is going to be like... That'll be like that. That's 3 generations. 1, 2, 3. Okay. Let's print family tree of blood types. Free memory. Okay, so we created what, a blank canvas of a family tree of 3 generations, which each person, which P points to person, create family points to person and the generation, and then we also need to hold that a person is attributed by 2 parents, then linked to person, but the character alleles is within that person. So you're going to have 2 characters within each person. If there are still generations left to create, okay, if generations is less than 1, okay, well, generations is 3. Oh, I forgot to do this. So what did I do here? I thought this already, okay, this creates, okay, these are just the tools. And then this, create a new family with 3 generations. So you created a family with 3 generations, and then create an individual with generations. Wait, how does this look with generations here? That's gonna be 3. The 3's in the parentheses of create family, the integer of 3, and it's linked to person. This is just a pointer pointing towards person. Person. Print family tree of blood types. Print family. Free memory. So, yeah, I think this, yeah. I think this just created a blank canvas of the family. And then this, and now we're creating the person of each family. Moloch size of person. So size of person is a structure and an character. Oh, okay. So, yeah. Okay. If there are still generations left to create, if generations less than 1, let's see what we then call print family to print out each of those family members and their blood types. Where is that at? Oh, that's this one. Oh, wait. What? Oh, I done skipped ahead somehow. Wait a second. Okay. Instructions. Oh, okay. Print out each of those family members and their blood types. What's the brand? By seeing providing some initial input to a random number generator, which will use random. Simulate the creation of a person structs for a family of 3 generations. A person, their parents, and their grandparents. Oh, a person, their parents, and their grandparents. Okay. Print family to print out each of those family members and their blood types. Find the function calls creation of a family. Okay. So this is just generating the system. It's generating the random alleles. I'm not gonna lie, this is a lot to take in right now. Jesus, this is kind of difficult. Okay. Alright, allocate memory for a new person. And then if there's still generations left to create, generation is greater. If generation's greater than 1, then it's going to keep creating because you already have the 1 person. So you're going to create, it's 3, and you're probably going to, take away 1 every time you create or something. And create 2 parents for the current person by recursively calling create family. Okay, yeah. Generation take away 1. Parent 0, parent 1. Create family. Set parent pointers for the current person. Okay. Create 2 new parents. Okay. Generations take away 1. So, new person, that's the new person I put up there. And then I need to make pointers from the parents to the person. Okay, so we have new person. What? Oh, it's not parent 0, it's parents. And then 0 here. That's kind of confusing. But those are 2 separate. Oh, okay. Oh, I see it now. Apparently, well, then the array of parents 0 equals parents 0. Okay. And then create an additional spot for the other parent. Parents. Okay. Well, where are we getting this array from? Parents, is that up here? Oh yeah, it's right here. Two parents per person. That's where that array is coming from. Okay, so this is it's in 2 arrays within a, what is it? A pointer. And then the array of both the parents 0 and parent 1. So, kind of gonna write this differently. So it's not really like this. It's more like parents, new person pointing down. And then we have an array of 2, because the third is null. And this is parents 0 and parents 1.
Look at you, faker. You're such a fake.
Parents 1. Okay. Alright. Randomly assign. Okay, so now we're doing the random stuff, which I guess that's just going to randomly generate what you want it to generate. Randomly assign current person's alleles based on the alleles of their parents. So it's the new person. this random generator thing. Like I'm not fully understand how that one totally works, but I know it has set to 0. I don't know what kind of context it leaves it under, but like this. Alright, so we have the area of alleles. The area of alleles is 2, with the last one being the null. Okay. Okay, so now this is when we're sending, we have it created here. These are the pointers, the person. No, wait. Well, isn't it the parents pointing to the person, not the person's pointing to the parents? Because that's what this is. This is a pointer. So the pointer of parent should be person pointing to the structure of person, right? Oh no, because now here sets parent pointers for current person. Okay, so we created pointers, and now we are setting who they're pointing to. So now new person is pointing to parents. 0 and 1, which is one area of parents that has now been defined as the parent 0 and parent 1 pointers. Okay. And then from here, new person also points at the array of alleles. And that's going to be 0 and 1. And they're both going to be the alleles. How do we say that? Okay. Person points to alleles, and parents also point to 2 alleles. So even the parents have alleles, which is defined the same way. So 0 and 1, and then 0. Okay. With that as a random generator, okay. Random. Remainder 2. I don't entirely understand how the random generator stays random and generate. Yeah. Alleles. assign current person's alleles based on the alleles of their parents. Okay, so new person's points to alleles equals the parents' alleles generated at random. Oh, so his allele 0 equals the parents' alleles generated at random for 2. So his 0 is going to be one of, but his 0 is going to be 0's parents. So this is going to equal that. This is going to equal that. Okay. If there are no generations left to create, okay, this was the loop. If generation is greater than 1, you started with 3 generations at 3. That takes away 2. That's going to leave it at 1, so it's only going to go through the cycle 1 time. I thought it was supposed to be 3 generations. I guess, I mean, that's only a person and their parents, but if there are no generations left to create, else sets parents pointers to null. Well, like in case? Why am I setting them? Let's say there are no more generations left to simulate. That is, generations equals 1. Yeah. If so, there will be no parent data for this person. Both parents of your new person should be set to null, and each allele should be generated random. I don't understand what we're setting the parents to null, though. Because that means... Okay, if there are no generations left, then new person... Hold on. Are you even... Is there a loop here? Oh, there's no loop. It just says if. So it's going to run through this once, and this is else if the parents, if there are no generations left to create. But there's not even a loop here, so why would it do anything other than, is there? I don't see a loop, I guess. I don't really see the point in this, because I can see that it's going to go through the if, but I guess this is like one of those scenario situations, like, because you always have to put if something's null. Randomly assign alleles. So parents not randomly assign alleles. I don't know. I'm trying to figure out how this picture is supposed to be drawn up. This is kind of difficult. Alleles. even then, you're creating two new parents from the person if there's still generations left to create. Then you're creating new parents. And if not, because then you're setting parents to null, but you're still generating random alleles. Completely random alleles. Randomly assign current person's alleles. Yeah, based on the alleles of their parents. Okay. I think I know. But this still isn't going to go back because it's not in a loop. So it's only going to do this and then go out. And if it doesn't do this, then it won't create parents. It'll just point a new person at the parents, but they'll be null, but it will generate the random alleles. I think. I feel like that's what I'm seeing. I don't know. I might be wrong. Crap gets confusing. Parent 0, 2 alleles. No, wait. Oh. No, this is just alleles and then random alleles. Oh, shit. Got one of those things going on. Oh. Okay. No, it's not going to do that anyways. Okay. Return newly created person. So. Return null? Don't you mean return? Yeah, return new person. Okay. I was tripping. Return new person. Alright, so it's only going to create one person in their family, basically. Because you're already starting off with 3 up here. And I don't see, any form of repetition. So, I don't really understand. But, complete the family tree function. Okay, so the free family function should accept as input a pointer to a person, free memory of that person, and then recursively free memory for all of their ancestors. Since this is a recursive function, this is a recursive function. Oh, it's like way down here. Okay, it's all. Oh, that's where the random allele comes from. Parents of current generation. Okay, there's a lot of extra going on down here. If parent generation is equal to 0, child's blood type, blah blah blah. Else generation equals 1, then print parents. And if generation is less than 2, wait. Oh, great. Oh, that's okay. That's how they had the great grandparents. Okay. Void free family, person P, which is up here. Free family, person P. That's the one we create. So this is the function that we created up here that we're using down here. Wait. so now we have this function that we're implementing. We are implementing it, right? Well, here's the main. Oh, okay, I see. Okay, so it runs this function first. I don't really know, but that's the one at bottom, right? Character random allele. That's the print family. That's a free family function. That's a create family. Okay, I guess that's just a random number generator. So first it runs this one, just the create family. Then it runs the print family, which is way down here. And then it runs free family. Okay. So this is after creating everything. Oh, this is a lot. And this should release it and give the memory back. Print it and then give the memory back. If P, if the pointer of the person equals null, worst case scenario, if something happens, something goes wrong, then we return. I thought you were supposed to return 1 or something. Okay. And then you have to free family. It looks like we have a recursive function here where P person is pointing to the parents. So this is freeing the parents recursively. So you're implementing the parents back into person, where if parents is null, then you free them. Or return. Now this is a lot, man. This is a lot to grasp. I don't know if I'm like, I kind of get it, but I'm not gonna lie. This is a lot. Let's see, parents. Okay. But how does this doesn't free the parents though? That only takes the parents, recurses it back into here, and then you're checking to see if parents is null, and if it is, then you return. And then free child, so then free the new person, or person, free person. Oh, if it's null, then you don't free it, or else you go through and free. Then you just return if there's an error, basically.
In this lab, your task is going to be to write a program in C that simulates the inheritance of blood type genes within a family. To give a little bit of science background, your blood type is determined by alleles. Alleles are different versions of a gene, and there are 3 different alleles with regard to blood type,
they're gonna be
called
randomly
A,
generated.
B, and O. Each person has 2 of these alleles. Maybe you have 2 A's, 2 B's, 2 O's, or maybe you mix and match, have an A and a B, or a B and an O, or an A and an O, for example. And when a parent has a child, each parent passes on one of their alleles to their child. So for example, if we imagine 2 parents, one that has a blood type of AB, and one who has a blood type of OO, then their child is going to inherit one blood type allele from each of their parents. For example, we might randomly choose A from one parent, and between the other parent O, and ultimately get a blood type of AO. But we also could have gotten a blood type of BO, for example. Which of the two alleles is passed on is just chosen at random. In order to simulate this type of inheritance inside of our program, we're going to need some sort of data structure that lets us represent the connection between people and their parents, as well as what alleles they have for their blood type. And because there is no type built into C to do just that, we can create a type of our own using a type def. So here, we have type def struct person, where every person is going to be represented by these two fields. Struct person star parents square bracket 2 means that every person is going to have an array of 2 parents, where each of those parents is going.
So once you create a person and you create their parents, those parents are going to also have parents already created, because the defining structure of a person has 2 parents that is already pointing at them. So every time you create a person, you're creating parents for them as well. Now, with the parents here, you're creating these parents, but then when this generation gets down to 1, and you run this once and you create 1 set of parents, those other parents also have parents, but those parents are going to be set to null. But this isn't a recursive function. This is only going to run once. So this doesn't look like, I mean, it doesn't look like it's going to do that. It just looks like it's going to run through this one time, because all you're doing is pulling this function here for generations 3. I still don't know where this is coming from. Indents length. Where's that? Oh, that's for the printing function. Yeah, they already did that part. And on base case, if P equals null, return print ident length. I wonder why they got that one set. Anyways.
Going to be a pointer to another person. Meanwhile, every person is also going to have.
Oh yeah, that's right. At the end of what, if you're trying to do like a linked list, at the end of the linked list, it has to be null. So that's why these are listed as null, because these are the grandparents are at the end, so they have to be labeled as null.
An array of 2 characters called alleles, representing which 2 alleles, A, B, or O, this particular person has. And because each person has 2 alleles, this is going to be an array of size 2 to represent both of those alleles. So in the example we saw before, we might, for this particular child, have the letter A stored at this child's alleles 0, and O stored at alleles 1. And meanwhile, parents 0 would point to one of the parents, and parents 1 would point to the other parent. Let's see how these pieces now would come together inside of the distribution code that we give to you for the lab. There's a fair amount of distribution code that we already give to you inside of inheritance.c, but let's try and distill it to just what's most important. Here, we'll notice that same type def, that we define a person as having pointers to 2 parents in this array of 2 pointers, and also having an array of 2 characters, representing the 2 alleles that this person has for their blood type.
Okay, then I got this backwards. It's not the parents that point at the person that points to the person that points to the parents. That's what I thought. Yeah. No, I did write that right. I don't know.
Next up is this relevant variable called constant generations, a constant integer, which is set equal to the number of 3. And this is going to represent the number of generations of data that we're going to simulate generating. In this case, we're simulating 3 generations worth of data for blood types, which means we're not just going to simulate the single child, but also generation 2, their parents, and also generation 3, that child's grandparents as well. We then have some prototypes for functions, but let's skip down to the main function to really see what it is that this program is doing. The main function is already written for you, nothing you need to do here, but we start by seeding the random number generator, just so that we're able to generate pseudo-random numbers, which is going to be useful because when we decide how genes are inherited, we want to be able to randomly choose which gene is going to be passed on from parent to child. Next, we call the create family function to create a family with a specified number of generations, returning a pointer to the most recent generation of person in that family. So if we create a family with 3 generations, we'll end up with a pointer to one person, but using their parent pointers, we could access that child's parents as well as that child's grandparents, but no further if we're only looking at a family with 3 generations. The create family function will be up to you to write, but the print family function we will write. After you've already created a family, we have already written for you a function that will take that family and print them out as a hierarchical family tree, printing out what blood type each of the people in that family has. Finally, you'll write the free family function, which will free all of the memory that you may have allocated in the process of creating this family. Because recall that for each of the people that you want to represent inside of your computer's memory, you'll likely need to allocate memory for them by using the malloc function to allocate some memory dynamically. But anytime you allocate memory with malloc, you'll also want to free that memory, giving it back to the computer so that it can be used for other purposes. Here then, in the create family function, is going to be what you'll implement, allocating memory for a new person, and then dealing with 2 possible cases. One, if there are potential parents that this child has that we need to recursively generate, or else if we're just generating a single generation, generating just a single person without any parent data. You'll also then write the free family function, which takes as input a pointer to a person P, and the task for this function is to free P as well as any ancestors of P. So if person P has parents or grandparents or other ancestors as well, you'll want to make sure to free them too. The print family function we've written for you, no need to do anything here. It takes a person and goes ahead and prints out their entire family tree along with their blood types. And this random allele function that we wrote might be helpful for you too. It randomly chooses an allele, A, B, or O, which can be useful if you get to a point where you need to randomly generate an allele to store inside of that alleles array. So with that distribution code in mind, let's then walk through what it is that your program is going to do. The first thing you should do is complete the create family function to create a family with a specified number of generations. In order to do so, the first thing you should do is allocate memory for a new person, calling malloc, passing in size of person to make sure you have enough memory for a new person, and then you'll use that person to potentially generate ancestors if there are more generations that you need to work with. So, if generations is greater than 1, meaning there are more generations that you need to generate, then you'll recursively create those previous generations. What does it mean to recursively create previous generations? Well, if you're trying to create a child that has 2 generations of parents, then you'll recursively call the create family function for each of those parents, where each one of those parents will have 1 generation of parents, and so on and so forth. So if generations is greater than 1, you'll want to recursively create those previous generations, and using the return value you get from those create family functions, you'll update this new person's parents, setting parents 0 equal to the result of 1 recursive call, and setting parents 1 equal to the result of some other recursive call. After you set that person's parents, recall that every person not only has 2 pointers to parents, but also has 2 alleles. So now you'll need to do the actual inheritance step, inheriting 1 allele from each parent at random. So you'll want to inherit the alleles from the parents by looking at one parent's 2 alleles, randomly choosing 1, and setting that as the child's allele 0, and then doing the same with the other parent, looking at their 2 alleles, randomly choosing 1, and using one of those as alleles square bracket 1, so that the child ends up with 2 alleles, 1 inherited from either parent. Otherwise, if generations is equal to 1, that means you're only generating 1 generation worth of family, that is, an individual person with no parents. And if that's the case, then both of the parent pointers should be set to null. And because there's nothing to inherit, because we don't have any data about the parents, you'll go ahead and randomly generate alleles for each of the 2 alleles for this particular person. And recall that in the distribution code, we give to you a function that will randomly generate those alleles. The final step for this lab is going to be to write the free family function to free all of that allocated memory. Recall that every time you called the create family function, you were calling malloc at least once in order to generate data for a new person to allocate memory for that person dynamically inside of the computer's heap. Now, after you've malloced that memory, it's your task at the end of the program to free all of that memory up and give it back to the computer. In order to do so, you'll want to first handle the base case. If the input to free family is null, there's no action you should take. You should never be freeing the null pointer. But after that, you'll want to deal with the recursive case, recursively freeing the parents, and then after that, freeing the child. How do you recursively free the parents? Well, you'll want to call the free family function on each of the child's two parents. Recursively then, that will also call free family on the child's grandparents and higher generations if there are other generations as well. And after those parents have been freed, then you can use free in order to free the child as well, ultimately freeing all of the memory that you've allocated throughout the program. After you've written these two functions, you should then be able to run your inheritance program in order to simulate the inheritance of blood types across multiple generations, seeing what blood types the grandparents had, seeing how those blood types translated into the blood types of the child's parent, and ultimately what blood type that child inherited as well. My name is Brian, and this was Inheritance.
Oh, shit. Or 68. Randomly assigned alleles. Oh, just the S. this looks hard.
In
I only talks about it for 2 minutes. God dang, what the heck? Looks like a lot of stuff, man. Crap. Okay, I gotta go to the restroom. Oh, man. For this problem, you'll implement that spell checks a file a la the below using a hash table. Crap. What's the hash table? Hash table is an array pointing to an array pointing to an array. Well, kind of. Hash table. Is an array damn it. Is an array where, like, say inside this array you have A, B, C, and let's say you select C, then C points to another array of A, B, C, D, whatever, you know, so on and so forth. And then that points to another array X, Y, Z or some shit. Okay. It's an array with a pointer pointing to another array. Okay. Let's see. This is how it's supposed to work. This is gonna be hard. Oh man. Okay. Alright, let's go ahead and download the cone. following folders. Okay. Given the many files in this program, it's important to read this section in its entirety before starting. You'll then know what to do and how to do it. I've been reading everything of everything, so, you know, whatever. Okay. Theoretically, on input of size n, an algorithm with a running time of n is asymptotically equivalent in terms of O. Whatever. To an algorithm with a running time of 2n, indeed, 2 steps. When describing the running time of an algorithm, we typically focus on the dominant, most impactful term. And in this case, since n could be much larger than 2. In the real world, though, the fact of the matter is that 2n feels twice as slow as n. The challenge ahead of you is to implement the fastest spell checker you can. By fastest, though, we're talking actual wall clock, not asymptotic time. In Speller.c, we put together a program that is designed to see. Put together a program that is designed to spell check a file after loading a dictionary of words from disk into memory. The dictionary, meanwhile, is implemented in a file called dictionary.c. It could just be implemented in speller.c, but as programs get more complex, it's often convenient to break them into multiple files. Okay, so they already have a program that does the spell check. And it could just be implemented as to break them into multiple files. The prototype for the function therein, meanwhile, are defined not in dictionary C, but itself in dictionary H instead. The prototypes for the function. That way, both Speller C and Dictionary C can include the file. Unfortunately, we didn't quite get around to implementing the loading part or checking part both, and a bit more we leave to you, but first a tour. Understanding. Dictionary.h. Open up dictionary.h. And you'll see some new syntax, including a few lines that mention dictionary H. No need to worry about those, but if curious, those lines just ensure that even though dictionary C and speller C, which you'll see in a moment, include this file, code will only compile it once. Next, notice we include a file called standard boolean. Okay, that's the file in which bool itself is defined. You've not needed it before since the CS50 library used to include that for you. Also notice our use of define, a preprocessor directive that defines a constant called length. Okay. It has a value of 45. It's a constant in the sense that you can accidentally change it in your own code. In fact, Clang will replace any length in your own code with literally 45. In other words, it's not a variable, just a find and replace trick. I finally noticed the prototypes for 5 functions: check, hash, load size, and unload. Notice how 3 of those take a pointer as an argument per the star symbol. So, check, load, and unload. Check, hash, load. Yeah. Okay. Unassigned integer of hash. Size. Unload is just a boolean. Load is a boolean. Check is a boolean. It's a word in the dictionary. So it checks the word for true or false. I mean, these are just the. So I guess this is just to link it all together. The char is what we use to call a string. Oh yeah, char word, char dictionary, char word, yeah. So those 3 prototypes are essentially just string word. And constant, meanwhile, just says those strings when passed in as arguments must remain constant. You won't be able to change them accidentally or otherwise. Okay, now open up Dictionary C. Okay. Notice how atop the file we've defined a structure called node. Node of the character word length +1. Structure node next. Okay. And we've declared global pointer array table. Oh. Okay. Oh crap. Dang it. I really want to knock this out, but I can't even stay awake right now. I should just take a nap. Because I can't. I'm falling asleep. God dang it. Oh, this is killing me. Yeah, I'm going to have to work on this one later. I'm about to fall asleep. Crap. Oh my god. Are you serious? No, this whole time? Was I even live? Was I ever live? I don't know, it says I was? What? I'm so confused. I wonder if it disconnected or something. On here it says 3 hours and 45 minutes? 2 hours and 45 minutes? Huh. It's very confusing. So confused right now. Was I even live? Like, I don't even know.